Okay, everyone, I wanted to take some time and to just give you a little bit more guidance towards problem 117 and therefore a little more guidance toward the design problem because the design problem in a way is linked to this one. All right, what's happening in problem 17 is that you have this compressor and they're saying, all right, well, the compressor is compressing air, right? Work consuming device. And if we look at a compressor, first law analysis results in mass flow rate. The work in is equal to mass flow rate times the change in enthalpy. Or you can look at it as MCP delta T. So what's happening is that the work in is causing a change in temperature of the air. And according to the second law analysis, what's happening is that the more inefficient the compressor is, the more work in's required, and therefore, according to first law, the higher the exit temperature coming out. So the minimum work that a pump can perform is the isentropic work. And we can look at that in the first law analysis where you have the change in entropy is equal to entropy carried in by mass and heat minus entropy out plus S gen. Or if we expand this out, we get some of the entropy going in by mass, some of the entropy out by mass, plus the sum of the entropy in by heat minus the sum of the entropy out by heat plus S gen. So if you look at an isentropic process at steady state, we have here for steady state, delta S system is 0. We have it being adiabatic and reversible, right? Definition of a isentropic process is adiabatic and reversible and also steady state. So we're left with 0 is equal to mass in entropy minus mass out entropy. If we have the same mass flow in and out, we end up with S in is equal to S out, which gives you the minimum possible change, or the best possible scenario, which gives you basically isentropic work, which is the minimum work. Now, the question comes in, okay, fine, I quantify my minimum work, there it is, I have it, great. But why would a problem ask you to see if you can actually decrease that work? Because the problem saying is like, all right, I have an isentropic pump. Now I want to find a way to make the compression power or the work required for compression less. So how much energy can I actually save? And what's that limiting case? And I think the confusion comes is, well, I thought isentropic compression was minimum work, so there's no way to save energy. And that's not exactly what they're asking. It's you can actually venture outside of the assumptions of isentropic and decrease work. And here's what I mean. Let me recast my first law. I'll recast my first law. Again, I'm going to recast a diagram here. There's what we looked at. What happens if I remove heat now? I know the problem is saying, all right, well, you know, I'm going to spray some water into this compressor. Will that decrease the required work to compress? I'm going to come back to that in a minute. All right, but let's look at what happens if I change the problem a little bit. It's sort of the same. It's the same thing, but let's look at it in terms of heat being removed from the compressor. All right. So here above in this section, we looked at just a typical compressor, minimum work in terms of an isentropic process. So we get a number. Great. Isentropic work is this much. Now, second scenario, I'm removing heat from the compressor as the air is being compressed. How does that change my first law analysis? Well, I end up with work in minus Q out equals delta H, or, you know, mass CP T2 minus T1. So I'll just leave it as CP T2 minus T1. M dot CP delta T. Okay, now it's no longer an isentropic process because I'm carrying entropy out of the system, right? I'm carrying entropy out of the system that results in this being a non-isentropic process. So what's happening as I remove more Q, my delta T is decreasing, right? My T2 is decreasing. To the limiting case, what do I mean by limiting case? I mean, the most that I can get is an isothermal process where I get T2 equaling T1. That results in MC delta T being 0 and my work in being Q out, right? In the case of an isothermal process. So the question comes is how can I make that happen? Where I get work in equals equal to work out for an isothermal process, right? I can quantify isothermal process pretty easily. In the back of your book, you'll see that the resultant equation to compute isothermal work is just MRT natural log P2 over P1. Now, okay, great. How do I know that this is actually happening in the case of this problem where I had water being sprayed into the airstream? What happens is that the water acts as a Q out. The water will be evaporated as the air is trying to be heated up. What is the most Q that I can get out of it? Well, in this case, the Q out is quantified as the change in phase of the water, right? I have a flow stream of water. Again, for MRT, this is mass flow rate of air. But for the water, I have mass flow rate of water times the exit state of the water and the inlet state of the water. If I assume the water to be saturated at 20 degrees Celsius, I get this resultant equation to be mass flow rate of water times state 2, which would be gas, state 1, which would be fluid, or simply HFG. So you look at HFG at 20 degrees Celsius, compute that, and see if it's true, based on the problem statement, the conditions of the problem, that this 0.2 kilograms per second of water is changing from liquid to gas. I find out what that heat rate is, what that Q is. I compute separately what my isothermal work is, throw it back, and see if not work yet. Sorry, Q in. Sorry. I look back and I see if my computed isothermal work is equal to this Q out, and see if that's true or not. Are they going to be exactly equal? No. But is it true that I have enough Q being taken out to equate it to be at least work in? In other words, if Q out is equal to or greater than work in, that means I am removing enough heat to make this process isothermal, basically resulting in the case being true that I'm actually able to remove heat from the compressor by throwing in a spray of air or a spray of water. So that means that my work in is going I can look at it as being isothermal, which is less than isentropic, and I can subtract one from the other, and I end up getting my total energy saved. And the only reason is because I am actually removing heat from the system. So now, you know, if I look back at this first law for the case down here on the bottom, is that I actually have a Q out going on. This should be Q in here. This should be Q out. So what happens is that my first law ends up being mass flow rate in, you know, if I, actually, you know what, I'm going to go ahead and recast my second law here. If I look at this, delta S system is equal to the sum of the mass in times entropy in minus the sum of the mass out times entropy out plus the sum of the Q in over T minus the sum of the Q out over T plus S gen. Well, I actually have a Q out term here, which results in my exit conditions changing. It's no longer isentropic. So I have a little bit of entropy being taken away from the system. So that means my temperature at the exit is less. Does that make sense? But the easier, the more direct way of looking at it is just in this terms here. I have work in minus Q out equals MCP delta T. And if I end up taking out enough Q to make it isothermal, I need to have a mechanism to remove enough heat in order to make that true. So I compute my isothermal work, I compute the amount of heat that I can remove, and if they're equal to each other or close to, I can assume the process to be more or less isothermal. And that's what I want you to also look at in the design problem. Now you'll notice in the, I just want to make a note that I changed the wording a little bit in the design problem so that it's a little bit more clear about what I'm looking for. But basically, I want you to be able to come to the conclusion and say, hey, listen, isothermal work is the minimum work that I can get out of this. So here are some proposed, here's why, you know, and recasting this first law this way and showing that, and then just describing some methods to which you can actually remove heat. And there's different ways that I want you to look up, and I want you to basically look at some forms of intercooling, which I'll explain. I'll have to explain later on Monday because it takes a little bit more of time to explain that than in a video. So Basically, go back, look at the design problem. I have reworded it to make it a little bit more clear about what I require from it. So I hope this helps, guys, and I will see you on Monday.